Hey everybody, a couple of problems from the problem set for section 8.2, day number 1, to go a little bit deeper into this idea of slope fields. So let's go ahead and get started here. Okay, so as I look at this question, 2008, number 27, non-calculator multiple choice, what you'll notice is we've got ourselves a slope field and a bunch of differential equations. And what we want to do is we want to match the slope field to one of those. Okay, so what I've found to be one of the easiest ways to do this is to identify, as you might remember, what I called isoclines and nullclines. Okay, so an isocline, what is that? That is a specific value that we choose to isolate for dy dx. So for example, I can say that dy dx equals 1. Okay, and if I isolate dy dx equal to 1, I could find those locations. Well, here's dy dx is equal to 1. It's not real helpful. That's not an isocline that extends along the differential equation, right? It'd be real nice if this entire line right here was an isocline where dy dx equaled 1, but it's not. So let's look at a nullcline. Let's look at dy dx equal to 0. And what you'll notice is that there are two linear functions that represent this nullcline. There's a linear function that I would call y equals 0. Okay, so what this tells me is that whenever y equals 0, dy dx equals 0. Okay, so let's highlight that color. There's another nullcline here, located at x equals -1. Okay, so what this tells us is that when x is equal to -1, then dy dx is equal to 0. Okay, so each of the differential equations below represent a different slope field. We're trying to isolate the one that satisfies these two criteria, which is that whenever y equals 0, dy dx equals 0, and whenever x equals -1, dy dx equals 0. Let's analyze our options here. Okay, I can clearly see that A is not going to work. And the reason that A is not going to work is because if x equals -1, we're not guaranteed that dy dx equals 0 unless y equals 0. So let's take, for example, the point here, -1, 2. Well, -1, 2 would give us a slope of -2. Therefore, that will not match this slope field. Okay, let's look at B. B, I can factor, giving me dy dx equals y times x minus 1. Okay, well, when y equals 0, dy dx equals 0, so we can satisfy the first criteria. But when x equals -1, if y is not equal to 0, dy dx would not equal 0. So if x equals -1 and y equals something other than 0, dy dx wouldn't equal 0, therefore it's out. Okay, let's analyze the third one. Let's factor. Let's pull out a y. That leaves us with an x plus 1. I like this one. Okay, so let's see if both criteria are met. When y equals 0, then dy dx would have to equal 0. When x equals -1, regardless of y's value, -1 plus 1 is equal to 0. Therefore, dy dx would equal 0. Therefore, Our answer would be C. Okay, I do want to look at E real quick. E could be a teaser or a distractor to make you think that this differential equation could represent or could be the match to that slope field. But dy dx here would satisfy the criteria for when x equals -1. However, this differential equation is not dependent on y. Therefore, it would not match our current slope field. All right, let's look at another example. Okay, here we are, 2004, Form B, number 5, parts A and B. It says, consider the differential equation dy dx equals x to the 4th times y minus 2. Okay, so what we can do here, you guys, is you can plug and chug. If you really want to, you could find dy dx at each of the, how many points is that? 12 points that are given. Okay, so you could start at the origin, which would be 0 to the 4th times 0 minus 2, which would be 0. Okay, and you could just kind of hammer out those all algebraically. Or you could use the idea of an isocline nullcline. And I'm going to focus specifically on nullclines. Okay, so check this out. I'm going to set dy dx equal to 0. Okay, this will actually kind of limit the amount of work I have to do. Okay, using the zero product property, either x to the 4th equals 0 or y minus 2 equals 0. Therefore, x would be equal to 0 or y would be equal to 2. Therefore, on the vertical line representing x equals 0, all slopes would be 0. And on the horizontal line, y equals 2. Therefore, all slopes along the horizontal line y equals 2 will equal 0. Now, that just took care of, 6 points for me. Now all I've got to do is knock out the other 6. Okay, so let's do those slopes. We'll find the slopes at those points. Slopes at the point 1, 0. Okay, 1, 0 will be 1 times 0 minus 2, which is a -2. Okay, so that would be a -2. 1, 1 will be a -1. I'm guessing 1, 3. Let's see what that would be. That'd be 1 times 1, which is a +1. And I'm just going to make a wild guess and say that there's going to be some symmetry here. Okay, so let's take a look at part B. It says, while the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are negative. Okay, this is really interesting. So if we look at the nature of dy dx, which is x squared y minus 2. Okay, we want to look and find where dy dx would be less than 0. Well, dy dx will be less than 0 whenever y is less than 2 and x is not equal to 0. Okay, so check out the nature of this function. I don't care really what x is as long as x isn't 0, right? Because if x is a negative value, x squared is positive. And actually, that should be x to the 4th. That's my bad. Okay. What I care about is when looking at this portion of the differential equation, because clearly this sets the magnitude positive or negative provided y is not equal to 2 and x is not equal to 0. Therefore, dy dx is less than 0 whenever y is less than 2 and x is not equal to 0. So if I were to kind of highlight that space in the graph, it would be any value, and this would continue on forever, kind of housed by this horizontal line here and this vertical line here. All right, very good. That's it for this video on 8.2 day number 1.